I'm Alan Fenn at MIT Lincoln Laboratory, and this is lecture number 14, Finite Arrays of Crossed V-Dipole Elements. This lecture is part of the lecture series Adaptive Antennas and Phased Arrays. Here's the course content breakdown by topic. This is lecture number 14. We'll be covering some phased array theory, and some antenna measurement techniques. We'll be taking into account array mutual coupling, and we will be looking at far-field characteristics. Chapter 14 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, can be used to supplement this lecture. So the purpose of this lecture is to describe measurements and simulations of finite arrays of crossed V-dipole antennas. Here's an outline of the talk. After a brief introduction and background, I'll describe the methods and materials, some results, and summarize. So by way of introduction, adaptive phased array antenna systems have been explored by numerous researchers since the 1950s. And the primary functions of a phased array antenna system are to provide rapid beam steering, in some cases multiple phase centers, and low side lobes. And so a phased array antenna consists of two or more transmitting or receiving antenna elements that can be used together to form a directional radiation pattern. So a phased array would consist of multiple antenna elements on some surface, could be planar or conformal. The elements are used coherently to form a directional beam. This slide shows an example radiation pattern for a typical phased array element that would have peak radiation at broadside scan and then would taper off away from broadside. So a typical scan sector might be defined as being 120 degree total scan angle, say from minus 60 to plus 60 degrees, with a peak at 0 degrees, which would be broadside to the array. The array pattern would be described by the product of the element pattern and the array factor. The normalized radiation intensity is equal to the array pattern magnitude squared, and the directivity is equal to the radiation intensity divided by the average radiation intensity. So in this lecture we're going to investigate the cross V-dipole. The diagram shown at the bottom shows a conventional straight dipole and a V-dipole. So the V-dipole has its arms swept back toward the ground plane at the angle alpha, and the terminals of the dipole are a distance h above the ground plane. Now cross dipoles in general can be used for dual linear polarization, or they can generate circular polarization. Straight dipoles, as shown here, can tend to have blind spots when they're located in an array and the beam is steered from broadside. This is due to currents flowing on the balun that can cancel the radiation coming from the dipole itself. Now sweeping the dipole arms back, forming a V-shaped dipole, can be used for wide-angle scanning phased array applications. So in this lecture, an experimental and theoretical investigation is conducted to verify the wide-angle scanning capability of V-dipole elements. So let's describe the methods and materials. So by way of review, this diagram shows array mutual coupling and the element gain pattern. So if we have an input feed to the central element of an array, where the surrounding elements are terminated in loads, we can measure the element gain pattern or calculate the element gain pattern. We can also measure or calculate the mutual coupling to the surrounding elements. So in this diagram, S0n represents the coupled signal from the central element to the surrounding nth element of the array. Now, by measuring or calculating the coupling coefficients in an array environment, we can then calculate the array's scan reflection coefficient by the equation shown here. It's the summation over the n elements in the array of the complex mutual coupling times a phase factor, which essentially steers the beam in the direction of the desired scan angle. We can measure the array gain or element gain by doing a gain comparison. So here's the phased array under test. There's a standard gain antenna used. Here's a source antenna. So what we would do is measure the test antenna radiation pattern and compare it to the standard gain antenna pattern, and the difference in amplitude between the two using a calibration curve would then tell us the absolute gain of the antenna under test. Now, in any phased array antenna design, we want to avoid undesired blind spots. These are angles where the element pattern has a null, or the array reflection coefficient approaches unity. So if we have a desired scan sector, we want to avoid any nulls in the element pattern. We'd like to have a pattern like this dashed curve, which would be smooth across the scan sector. Or in the case of the reflection coefficient, we'd like to avoid large peaks in amplitude. Now, the radiation pattern of a V-dipole antenna can be calculated in closed form. This is for an isolated V-dipole antenna over a ground plane. And so this equation is derived in chapter 14 of the book. And basically what we have is, for the case where the currents are sinusoidal on the arms of the dipole, we can add up the contributions from the left and right arms of the dipole to arrive at this expression shown here. This equation depends on the tilt angle alpha of the dipole arms. We can model an array of V-dipole antennas conveniently using the method of moments with sinusoidal basis functions. So in this lecture, we're using an E-plane model where the dipoles are shown as here, or an H-plane model as shown here. So in this lecture, for convenience, we analyze the cross-dipole array by using an E-plane model for one polarization of the dipole, and we use an H-plane model for the other polarization of the cross-dipoles. So each of the principal V-dipoles has an image dipole in the ground plane. Here are photographs of a straight-arm dipole and a V-dipole antenna. And these are prototypes for L-band covering the 1.2 to 1.4 gigahertz band. And so the way this antenna is constructed is, here is the input coaxial feed. There are two feeds for each of the dipoles, and then there's a double-sided printed circuit board at the top which makes the electrical connection between the arms of the dipoles. And there's a crossover point. These are separated by the thickness of the dielectric board. The V-dipole that was built has a 45-degree arm tilt angle, and the dipoles are made with microstrip line printed on a printed circuit board. Now, this slide shows the 19-element V-dipole array that was fabricated. So it's in a hexagonal lattice. The array was located at the center of a 1.22 meter ground plane, and mutual coupling measurements between the dipoles was conducted, and element gain patterns were also measured. So let's show some results. First, we show the moment method calculated E-plane patterns for the center element of a 19-element V-dipole array. This is the E-plane model, and what we want to show here is that one unknown is a good approximation for the radiation pattern over plus or minus 60 degrees. So we're comparing one unknown to three unknowns, and there's very little difference over the 120-degree field of view of this antenna for the E theta polarization. And so in this slide, what we want to show is the difference between a straight-arm dipole and a V-dipole. So these are single isolated dipoles on the center of a 1.22 meter ground plane, so 1.3 gigahertz, and there is a large effect in sweeping the arms. And so a straight dipole antenna, shown here as the dashed curve, has a fairly narrow radiation pattern compared to the V-dipole, which has a broad pattern. So the effect of sweeping the arms down toward the ground plane broadens the element pattern, and this will be advantageous for a phased array for getting wide-angle steering. So in summary, we see a broader E-plane radiation pattern for the V-dipole antenna compared to a straight dipole. Now in the H-plane, there is very little difference between the straight-arm dipole and the V-dipole. So this slide shows the measured H-plane patterns for a single straight-arm dipole and a single V-dipole on the 1.22 meters square ground plane. And we see there's very little difference in the measured gain pattern for these two types of antennas. So in summary, the H-plane patterns are similar for straight and V-dipole antennas. Now we show the measured V-dipole array mutual coupling. This is for the center element of a 19-element hexagonal array. So we're driving the center element, and we measure the amplitude and phase to the surrounding neighbors. And so in this slide we see that the coupling to the nearest neighbor in the collinear direction is down minus 25.5 dB, and in the direction where the elements are relatively parallel, we see stronger coupling, which is minus 19.7 dB to the nearest neighbor. So using these measured amplitude and phase coupling coefficients, we can calculate the array scan reflection coefficient. And that's shown here. So the scan reflection coefficient has been calculated from the measured mutual coupling coefficients for the V-dipole array. And so in the E-plane scan, we see that the reflection coefficient magnitude is approximately 0.3 out to about 45 degrees, and then it starts to increase. In the H-plane, the scan reflection coefficient is on the order of 0.25, and it starts to increase when the scan angle is reaching 50 degrees or more. We can calculate the mismatch loss from the reflection coefficient, and the mismatch loss is typically on the order of about a half a dB out to about a 45 degree scan angle. Now this slide shows the measured and calculated center element gain patterns for the V-dipole array. We see there's very good agreement between measurements and calculations. The peak gain occurs at 0 degrees, and we see broad radiation pattern coverage over plus or minus 60 degrees as desired in a wide-angle steering phased array. There's no evidence of a blind spot for this type of radiating element. So let's summarize. Phased array antenna elements using V-dipoles have been described in this lecture. Array mutual coupling and element gain patterns for an example V-dipole array have been shown. And the V-dipole element exhibits good scanning capability out to wide scan angles. Chapter 14 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, contains additional information that can be used to supplement this lecture.